Hello, we're back. I have red on my paper because I was taping and then my video stopped. So I'm doing take 2. What I will do is tell you what I wanted you to know, which is these 3 examples, including this one, so the 4th example, so all 4 examples are a way to say the same thing in different ways. This is a picture, okay? But this information, in terms of its outcomes, is organized in a table, and the table is visually represented by the graph called the probability distribution, okay? So what some students forget is that this is called a probability. So C is called a probability distribution, okay? The graph. Right? The other thing you want to know is that the 4th way of organizing this information, okay, is the expanded binomial. So there are 4 ways, 1, 2, 3, 4, of saying the same thing, just in different visual representations. All right. There are 3 ways to find the probability of a binomial experiment: a tree diagram, a binomial expansion, and a formula. Now, a tree diagram can also lead you to relative frequency, in a table of values. Okay? It can also give you, because you're finding, right? So a tree diagram can give you the relative frequency in a table of values, which also lead to a probability distribution. Just one eye there. Okay, so to find the probability distribution, you have a tree diagram, you have a binomial expansion, and a formula. This binomial expansion, okay, right here, gave you the same information that your tree diagram did, right? Alrighty, so we have 3 ways: a tree diagram, a binomial expansion, and a formula, which looks like this. So it says the probability of the discrete random variable taking on specific values. In this case, it would be the discrete random variable would be the outcomes of a coin flip done 3 times, is equal to the possible outcomes, which would little x be equal to 0 heads, 1 head, 2 heads, and 3 heads. That probability, okay, those probabilities are equal to n choose x, where n is the number of trials, x is the value that is described in this bracket, times p, the probability of being successful to the power of x, times q, the probability of being unsuccessful to the power of n minus x. But if we sub in the probability of being unsuccessful as 1 minus p, okay, then we can still write the probability of the discrete random variable taking on different values of x is equal to n choose x times p to the power of x, where q now is 1 minus p, because q is being replaced by 1 minus p to the power of n minus x. Some people say, well, why do you do that? Well, because if you know p, then it's easy to find what 1 minus p is, all right? So, as I've described in words, I've described on paper, where the capital letter X represents a discrete random variable. In this case, it's the number of heads in 3 coin flips, where little x represents the values of the discrete random variable. In our case, it's the values of 0, 1, 2, and 3, 4, because that's the different values of number of heads, where n represents the number of trials in our experiment. In this case, it's 3. And p represents the probability of success. In this case, it's 1/2. Now, that was fairly quickly, but I'm going to show you how to break it down. We're going to use the formula, which is exactly this from here, okay, to determine the individual probabilities, okay? So we're going to define the individual. So determine finding the individual probabilities for little x to be 0, 1, 2, and 3. So this is always little x. Okay, it's always little x. So the capital X is thought of as the name of the experiment. So what is the experiment? Well, it's the experiment where we toss the coin 3 times to see how many heads we get, okay? So we can write that the probability, the individual probability of X taking on this specific value of 0 is equal to this right here. So n choose X times P to the power of X times 1 minus P, sorry, we're going to use this one, 1 minus P to the power of n minus X, okay? So we're going to sub in the values of n, where n is the number of trials, so 3 trials. X is the little x, okay, so little x, so this is capital X equals little x for the probability. So what we're doing is we're taking this, okay, we're taking this right here, and we're writing it, okay? All right, so we're subbing in n is the number of trials, where X is now 0 heads, because they're individual probabilities, times the probability of getting the head. So P is the probability of getting 0 heads, right, is equal to 1 head out of 2 total outcomes. Okay, because we can get a head, or you can get a tail. Running out of room here. Okay, so we're going to sub these in. Okay, so it's equal to n, where n is 3, x, where x is 0, times the probability of 1/2, probability of 1/2, to the power of x, where x is 0, 1 minus the probability of p, which is 1/2, to the power of n, which is 3, minus x, which is 0. So 3 choose 0 to the power of 1/2, times 1/2 to the power of x. 1 minus 1/2 is 1/2, and 3 minus 0 is 3. Okay, so 3 choose 0. 3 choose 0 is 1. 1/2 to the 0 is 1. 1/2 cubed is 1/8. So 1 times 1 times 1, these are all over 1s, is 1, and 1 times 1 times 8 is 8. So the probability of getting 0 heads is 1/8. Probability of getting 0 heads is 1/8, right? All right, what's the probability of the discrete random variable specifically equaling 1? So this is little x, capital X, probability, okay, is equal to n choose x times the probability of x to the power of x, 1 minus the probability to the power of n minus x. And you'll notice that the only thing that changes is little x. N is still the number of trials in our experiment, which are 3 trials. Okay, little x is 1 now, because it's for the individual probability of getting 1 head. Probability of getting 1 head is still 1/2. Okay? All right, so let's do it. So this is equal to n, where n is 3, little x is 1. probability is 1/2, raised to the power of x, where x is 1, 1 minus p, where p is 1/2, n is 3, minus the x value, which is 1. So we get n choose, 3 choose 1. 3 choose 1 is 3. 1/2 to the power of 1 is 1/2. 1 minus 1/2 is 1/2. 3 minus 1 is 2. So you get 3 times 1/2 times 1/2 squared is 1/2 times 1/2, which is 1 over 4. It's over 1. So we get 3 times 1 times 1 is 3. 1 times 2 times 4 is 8. Okay? So therefore, the probability of getting 1 head is equal to 3/8. Okay? All right, what about the probability of getting exactly 2 heads? Well, that's when the discrete random variable is equal to 2, and that's equal to n choose x times the probability of p to the x, 1 minus p to the power of n minus x. And like I said, the only value that's changing here is little x, right? Subbing in n is the number of trials, still 3. Little x is just now taking on the value. This is still big X equals little x. Okay, this is probability. So x here is 2. 2 heads. And p is the probability of getting 2 heads. Okay. Sorry. Probability always is the individual. My mistake. Okay. Probably getting 1 head. So even though your x value, your discrete random variable, takes on a larger value, your probability is unchanged, which is the definition of a Bernoulli experiment or Bernoulli trial. Okay, so it's still, okay, so you're still having 1 head out of the total number of outcomes. Okay, sub those in, you get 3 choose x, where x is 2. Probability cannot change. Okay, so that was my mistake where I was changing it to consider the whole total. It's not. It's an individual probability. Okay, so it's 1/2 to the power of x, where x is 2. 1 minus 1/2 to the power of n, where n is 3, minus x, where x is 2. So 3 choose 2. 3 choose 2 is 3. 1/2 squared is 1/2 times 1/2, which is 1/4. 1 minus 1/2 is 1/2. 3 minus 2 is 1. So you get, that's over 1, right? So you get 3 times 1 times 1. That's still just 1. So that's 3 over 1 times 4 times 2 is 8. Okay, so the probability of getting 2 heads is 3/8. Okay, these are individual probabilities. Probability of getting a discrete random variable where it equals specifically 3 is equal to, and choose x, little x, times the, oops, shoot, okay, you didn't see that. So I subbed in n for 3, x, little x is 2 because 2 is in the brackets there. P is the probability of 1/2, x is the value of 2 heads, 1 minus p, where p is 1/2, n is the number of trials, which is 3, x is the number of heads, which is 2. 3 choose 2. 3 choose 2 is 3. Okay. 1/2 squared is 1/4. 1 minus 1/2 is 1/2, and then 3 minus 2 is 1. And then multiply the numerators. 3 times 1 times 1 is 3. Denominators multiplied 1 times 4 times 2 is 8. So the probability of getting 2, so this number there is always this number here, okay, is equal to 3/8. Okay, individual probabilities. Okay, what's the probability of the discrete random variable equaling 3, where that means that we get 3 heads and 3 coin tosses? It's equal to the n choose x times p to the power of little x, 1 minus p to the power of n minus x. Summing in a value of little x, well, we'll do it in the order that we've been doing it. N is 3 trials. Okay, and remember, if it's capital X, then the number it's equal to is little x. Okay, so it's always little x in the brackets. So N is 3 trials, little x is 3 in this case, 3 heads. The probability is always the probability of just getting the one individual head on the individual coin toss, okay? So this is not changing. This probability cannot change by definition, okay? So it's 1 head out of 2 possible outcomes, right? A head or a tail. Okay, so it's a head or a tail. Okay, so the probability is 1/2. Okay, all right, so n, where n is 3, choose x, where x is 3, times the probability of 1/2. That is not changing to the power of x, which is 3. 1 minus the probability is 1/2. N is 3, x is 3. So 3 choose 3. 3 choose 3 is 1. 1/2 cubed is 1/2 times 1/2 times 1/2, which is 1/8. No LCD required. Multiply the numerators, multiply the denominators. 1 minus 1/2 is 1/2. 3 minus 3 is 0. So you get 1 times 1/8. Anything to the power of 0 is 1. So this is over 1, this is over 1. 1 times 1 times 1 is 1. 1 times 8 times 1 is 8. Okay, so therefore the probability of getting 3 heads is equal to 1/8. Okay, so the question is, where have you seen the values in I, double I, triple I, and IV before? Okay. Where have you seen 1/8, 3/8, 3/8, and 1/8? You've seen them here. 1/8, 3/8, 3/8, 1/8. 1/8, 3/8, 3/8, 1/8. 1/8, 3/8, 3/8, 1/8. And then this information is also here, but it's not organized, right? Not organized in a sense that it's totaled. Okay? So have we seen these before? We've seen these values on page 1 when we found the relative frequencies graphed probability distribution and expanded the binomial a plus b to the power of 3. Okay? All right. Please try this seat work. I will photocopy the pages and upload them as images to attach to the lesson. Email me, please, if you're having problems.